Hi, it's Mr. T here. In this video we're going to look at the periodic trends of atomic radius, how the atomic radius changes across a period and down a group. So this idea is included in the Achievement Standard 91390 for NCEA, Level 3 for Chemistry, and we'll go over what's needed to know for that standard. Okay, so let's have a look at some plots of the atomic radius. So you can see on the right here is a graph, and the graph depicts the atomic number along the bottom against the radius of an atom. Now, if we plot the atomic number against the radius, we get the following trend. So the trend is that we see when we go across a period from lithium to neon, we see a decrease in the radius of the atom, or decrease in atomic radius. When we go across a period from sodium to argon, we also see a decrease in atomic radius. And actually, every time we go across a period in the periodic table, we will see a decrease in the radius. If we look at a specific group, so in this case, let's say that we looked at lithium, sodium, potassium, or we looked at helium, neon, or argon. So let's look at helium, neon, or argon. We can see as we go down a group, so as we go downways, the actual atomic radius increases. As we go down from lithium to potassium, we also see an increase in atomic radius. So down a group, we get an increase in atomic radius, but across a period, we get a decrease. Now, we're going to have to explain the reasons for this, and we will in the next couple of slides. So, what is the atomic radius? Well, due to the nature of the cloud of electrons that surrounds the nucleus, it's quite difficult to tell exactly where the cloud specifically ends. So what we end up doing is taking two identical atoms that are bonded together and measure the distance between the nucleus of two adjacent atoms. And if we half that distance, that is the radius. So the radius is defined, the atomic radius is measured as half the distance between the nuclei of two identical bonded atoms. Now, if we go across a period, so here I'm going from lithium, across the second period from lithium to carbon to fluorine, what actually happens is we keep the same number of energy levels. We have a number one energy level and a second energy level in all three atoms. However, the outside valence electron feels a stronger attraction in fluorine than it does in lithium, because the nucleus in fluorine has a positive charge of 9, a very strong nuclear charge, where lithium only has a positive charge of 3. So the electrons on the outside, or the valence shell of fluorine, experience a stronger electrostatic attraction and therefore are pulled in closer than what they would do if they were electrons in the valence level of lithium. So as we go across a period, the nuclear charge increases, the strength of the electrostatic attraction increases, and the valence electrons are pulled in closer to the nucleus. Hence, we have a reduction in the atomic radius as we go across the period. Okay, what if we go down a group? Well, down a group is a bit more straightforward in one aspect, though it does have there is a caveat or something we need to include when we talk about it. So if we go down a period from lithium to sodium to potassium, this is the first period or the first column on the periodic table. Notice that what happens every step we go down in the period, we add another energy level. Now, because we are adding another energy level, we are automatically increasing the radius of the atom. So going down the period, the radius increases because we increase the energy level. We will note, however, that as we go down the period, the positive charge still increases. So that would have an effect of pulling the electrons in closer, but that effect is not as strong or noticeable as the extra energy levels that are added. So we would mention it, but we would clearly state that it's actually the extra energy levels that causes the increase in atomic radius. So the nuclear charge does get stronger, but it's not important. Okay, what if we were to talk about how does the radius change when we go from an atom to an ion? Well, when we go from an atom to a positive ion, the charge in the middle, the nuclear charge, stays the same. But what we do is we lose the valence electrons. So in this case, in lithium, we lose the second energy level. And we can quite clearly see when we lose an energy level, the ion is significantly smaller than the atom. We don't have to worry about any effect of the nuclear charge because it's exactly the same. But we do have a decrease in the size of the ion compared to the atom. If we go to a negative ion, an anion, it's a wee bit more complicated. So what happens here is we have to kind of think about atoms and ions, their outside valence shell, as electrons want to have their own space and they push against other electrons. We say they are mutually repel. If we try and add more electrons into the same energy level, there is a small inflation of the energy level as the electrons exert their negative repulsion against other electrons and they push out slowly. And this, we can think of this analogy if we had a group of people holding hands in a circle, like 5 people. If we added another person within that circle to make it 6 people, the circle would actually get bigger and expand because we added something extra into that space. Now this happens because electrons mutually repel each other, or mutually repulsion, and push the valence level out a bit further. So these are the 4 ideas that we need to be able to explain. So let's just summarize those again. So the atomic radius decreases across a period and increases down a group. There are 3 factors that affect this. Energy levels. If you gain energy levels, which you do as you go down a group, you will increase your radius. If you lose an energy level, as you will do if you go from an atom to a positive ion, you will decrease your radius. Nuclear charge. As we go across a period, the atomic number increases and hence the number of protons or the nuclear charge in the nucleus increases. This creates a stronger attraction to the valence electrons and that level is pulled closer to the nucleus, reducing the radius. Mutual repulsion. Remember, when we go from an atom to a negative ion, an anion, then what happens is we gain electrons in the valence levels. They take up more space because of mutual repulsion and we expand the level a little bit, increasing the radius. So these 3 ideas of how energy levels, nuclear charge and mutual repulsion affect atomic radius are pivotal in being able to explain the difference in atomic radius between any 2 atoms. Let's quickly look at a couple of examples. So let's use the knowledge that I've just gone over in the last slide to identify and justify the difference in atomic radius of nitrogen and fluorine. So nitrogen has a greater radius than fluorine. We know that because as we go across the periodic table, and these 2 are in period 2, the atomic radius decreases, so fluorine must have a very small atomic radius. Both atoms have valence electrons in the second energy level because they're both in the second period of the periodic table. So energy levels does not affect the difference in radius. So I'm saying that this statement is not relevant. It's not that it's not relevant, it's possibly not the correct word here, but you need to show anybody who you're explaining that you understand that valence electron levels are important, but in this case they're not because they have the same number of valence electrons levels. Now we write the relevant statement. Fluorine has 9 protons compared to nitrogen 7. As fluorine has a larger nuclear charge, there is a stronger attraction to the electrons in the valence level, pulling anything closer and making fluorine have a smaller radius than nitrogen. And that's our relevant explanation, but here is our full explanation with a statement, the part that's not relevant but important, and the part that's relevant. Let's have a look at another example. This was across a period down a group. Okay, so we want to use our knowledge to explain the difference in atomic radius of oxygen and sulfur. Okay, so the first thing, sulfur has a greater atomic radius than oxygen. That's because as we go down a period, the atomic radius increases. Now the reason for it, sulfur has valence electrons in the third energy level, where oxygen has them in the second energy level. Therefore, sulfur has a larger radius due to having an extra energy level. So it's quite a clear statement here. It's an extra energy level that makes it larger, but let's just write the non-relevant bit, or the bit that we also need to say that we know that this would make an effect, but it doesn't in this case. So sulfur does have more protons. It has 16, oxygen has 8. However, the number of protons does not counter the effect of an extra energy level. Or we could say it another way and say it's not as important as the extra energy level. Look, I hope this video has helped summarize your understanding of atomic radius. Look out for my other videos on periodic trends and other aspects to do with chemistry. Good luck and see you later.